So another way that we can try to reduce the test set error of a network or the generalization error, even though it's not going to fit the training set as well, is to use what's called dropout. So at each step of training, dropout applies one step of backpropagation learning to a new version of the network that is created by deactivating a randomly chosen subset of the neurons. So essentially, this is almost the same as training a large ensemble of different networks, where each time you're randomly picking a new architecture by eliminating some neurons from the base network. So more specifically, assume, for example, we're using a stochastic gradient descent with mini batch size M. For each mini batch, the dropout algorithm applies the following steps for every node in the network. First, with probability P that we set before the start of training, the unit output is multiplied by a factor of 1 over P. Otherwise, the unit output is fixed at 0. So the dropout essentially is typically applied to units in the hidden layers with a probability of 0.5. So for input units, we put a probability that's higher of 0.8 because we don't want to lose an input to the network. Typically, we don't want to use an input feature, but we don't mind losing a hidden neuron. So by applying this process, we produce a smaller network with about half the number of neurons that we started with, to which we apply backpropagation with the mini batch of M training example. We repeat this process until the training is complete. And then when we're running the test set, when we're getting predictions over the test set, we don't apply any dropout. Now, why this works, there are different ways to explain why this works. One way is to say that by introducing noise, this random noise, during training, the model or the network is forced to become robust to noise. So the network every time has to adapt to a new set of neurons, which forces it to become robust at losing one or more neurons. So that's one possible explanation why dropout works so well. Another possible explanation, like we said earlier, is that dropout approximates the creation of a large ensemble of smaller networks. And when people tested this hypothesis, actually it turns out to be true. Okay, that actually what's happening is that these smaller networks end up each having a vote essentially in the final overall network, where remember we don't apply dropout during prediction over the test set. Another explanation for why dropout works is that hidden units that are trained with dropout must learn not only to be useful hidden units, they must also learn to be compatible with many other possible sets of other hidden units, which may or may not be included in the full model. So this is similar to the selection process that guides the evolution of genes, like in genetic algorithm. Each gene must not only be effective in its own function, but must work well with other genes. whose identity in future iterations may vary very much. Another explanation why dropout works is that dropout applied to later layers in a deep network forces the final decision to be made robustly by paying attention to all of the abstract features of the example, rather than focusing on just one and ignoring the others. For example, let's say we have a classifier for animal images that is able to achieve high performance on the training set by just looking at the animal's nose. This network would probably fail on a test case where the nose was not really clear in the image, right? Or maybe it was damaged somehow. Now with dropout in training, there will be training cases where the internal or hidden unit, let's call it the nose unit, which was responsible for detecting the nose in the image, is zeroed out. Remember that nodes are eliminated randomly. So it's very possible that in that specific subnetwork, the network has to learn to identify what's in the image without having access to this nose unit, which causes the learning process to find other clues or other features to identify what's in the image. So notice that trying to achieve the same degree of robustness by adding noise to the input data would be difficult, because there's no easy way to know in advance what the network will focus on. How can you force a network to focus on noses, for example, in this case? So there's no easy way to delete the nose automatically from each image, to say I'm just going to add noise to the input and force the network to learn to identify what's in the image without a nose. So essentially, dropout forces the model to learn multiple, robust explanation for each input. This causes the model to generalize well, but also makes it more difficult to fit the training set. It's usually required to use a larger model and to train it for more iteration. So we start with a much bigger network in that case, and then using the probability of dropout, we determine, how many hidden layers, how many hidden units will be eliminated in each iteration, and we let it train longer. But at the end of the day, we obtain a model that maybe doesn't fit the training data very well, but would do much better at during test time and generalization. So now that we've covered all the practical issues associated with training deep neural networks, we talked about all the different regularization approaches. We talked about different ways to select the best network architecture for a given problem. We also talked about a specific architecture that is used for computer vision and image input, which is the convolution neural network. We explained how the concept of convolution works using pooling and convolution layers. Now we're going to talk about a different type of architecture that is specifically used for time series data. So data that comes in a sequence rather than in a snapshot like a photo or an image. So this will help us with problems like translation, text translation, or if you work in the stock market or anything that involves time series analysis, this is also essential. And and other applications. So let's stop here and then start in the next video since we don't cut it.